Hello everyone, welcome back to ECE100, Introduction to Electrical Engineering. This is class 9. In this class we're going to talk about series equivalent resistance and voltage divider. So when you look for series element, how do you know that the elements or circuit elements are connected in series? So the one condition for series connection is that all series element shares the same current. So if you write here, all series elements share the same current. So that means if I have this, let's say, and if I have also this here, if I connect them with a source that's supplying current here, let's say it's current I come in here and current I1 go in here, current I2 go in here, and let's name it R1, R2, R3. If you look at here that R1 and R2, they have same current I1 going through them. That means that R1 and R2, they're in series, but R3 is not in series with R1 and R2 because R3 has a different current. So R1 and R2 are in series. All right. So that means if the elements are connected in series, they share the same current. All right. So if we have more than one element connected in series, like resistance, more than one resistance are connected in series, and what is the equivalent resistance of that connection? So R equivalent for series connection is basically you add all resistance connected in series. So I could be 1 through n. So you add all the resistance connected in series, they will get the equivalent resistance. So that could be here R1, R2, R3, all the way to Rn. All right, so that's how you find the series equivalent resistance. So if we apply that formula over here, for this one, you can see that you have three elements connected in series because if you have a current over here, that same current will go through all three of them. Again, if you have a current over here, that's also same current going through all the elements. So if you add all three of them, obviously you get 425 ohms. And if we add all four of them here, you should get, so those are the equivalent resistance for these two connections. All right, so equivalent resistance and voltage divider, series connection and voltage divider, they go side by side. So let's see that, let's do some notation here. There's the voltage over here is V1, voltage across this one is V2, voltage across this one is V3, right? So now our equivalent for this connection would be R1, R2, R3. And for the current going over here, same current for all three of them because the series connection, that would be supply voltage Vs over R equivalent, right? So now, if I look for V1, V1 right here, voltage drop across R1, that should be V1 equal to same current I times R1, right? So then V2 over here, it would be same current because same current going through all the resistor R2. So simple Ohm's law. And V3 would be I R3. So now if I take this one more step over here, what is I? I is your Vs over R EQ times R1. If I rearrange that, that should be Vs times R1 over R EQ. So that is your V1, and same your V2 over here would be Vs R2 over Req, and over here your Vs would be R3 over Req. So you can see that all three format, there's a common thing. Vs is the common there, Req is equivalent resistance common there, only changing R1, R2, R3. That means for any series connections, if I now try to find a voltage for a particular resistance, let's say it's I could be any number, that should be Vs, look at here, then this one will be Ri over Req. So that is the common generic equation for voltage divider. That's a very generic equation for voltage divider. So again, for the generic equation is Vi is Vs is supply voltage to the series connection, and should be Ri over R equivalent. R equivalent is your equivalent resistance of the series connections. So it could be 1, 2, 3 all the way to n. All right, that's the generic equation for voltage divider. We can do this example in the class. Also do this example in the class. And let's talk about the power dissipation and power sharing for series connected resistor. Remember that power equation has three format. P equal to VI, we discussed them in the previous classes, and I squared R and V squared over R. So for example, let's say this is your, over here, this is your V1, let's say this is your R1, and also let's say P1 here. So this one is, let's say R2, over here is a V2, P2, and over here let's see is R3, over here is V3, P3. So if I do it over here, let's say for example P1, it would be V1 squared over R1, right? Or I can also say that it would be I1 squared R1, right? So that is the power dissipated by resistor R1. Hopefully you can see what I'm trying to do here. So, and your I1 is basically same for all the resistor, because this is same current going through all of them. So I can basically say that over here is I squared, right? Just correcting that. So the same current going through all the resistor because it's connection, right? And your I, if the previous slide you have seen that I is Vs over Req, right? So if I can now rearrange this equation over here, P1 is Vs over Req squared R1, right? Or if I go one step ahead, I can say that is Vs squared over Req times R1 over Req. I just rearranged the equation, right? And this one over here is basically 12 power. Vs squared by Req is, if we use this equation over here, is 12 power. R1 over Req, right? So with that, if I come over here, this slide over here, let's say I can write the same equation P2 to be PS R2 over R equivalent. I can write it for P3 PS R3 over R equivalent, right? So now in generic form, I can now write Pi, I could be any number here. It would be PS Ri over R equivalent. So this is the generic form of the power division, power sharing among the series resistance connection. This is very close. This is very similar to your voltage division. So again, now I can write over here. So Pi is PS Ri over R equivalent, and also now you remember that Vi would be what? PS Ri over R equivalent. So you can see that these two equations are basically similar to each other. We're going to do this problem.